This is my lab report for Lab 5, Choose Your Own Adventure. For my lab, we're working with perfectly elastic collisions. We will use energy conservation principle, momentum conservation, and position update. We will analyze a video found online, found on YouTube, and we will make a model using GlowScript. The video we will analyze comes from Dan Burns, and the inspiration for the model comes from 3 Blue, 1 Brown. A brief summary. We found that collisions conserve momentum, and that in our model, kinetic energy was also perfectly conserved. All right, our principles. So for all collisions, momentum is conserved. This means that final momentum is equal to initial momentum. And for perfectly elastic collisions, kinetic energy is also conserved. So Kf equals Ki. And down here you can see all of our derivations for the equations that we will be using in our model. And on the right, there's position update. Our model assumptions and reasonings. So we will say that only collisions will affect our motion. That means no friction, no drag, nothing of that nature. And that the masses of the barrier walls are so large that they can be considered stationary. And we will, of course, be assuming perfectly elastic collisions. System versus surroundings. For our model, the system is the 2 blocks, surroundings are the barrier walls. For the experiment, the system is 2 bowling balls, and surroundings are the earth, the rope, and the air. Our initial conditions for both the model and the experiment are shown on screen right now. For our experiment, we hang 2 balls up so that they sort of resemble Newton's cradle, as you can see on the right, and then we pull 1 ball to the side and then let it go. And then we record the motion of the balls, and then we analyze that video using Tracker. For our model, we first set all of our visualization stuff, and then we do our initial conditions. And then here in the iteration, if the block hits a wall, we will say it gets reflected back with the same velocity in the opposite direction. And then we check if there's a collision. If there is, and we will calculate the new velocities of the 2 blocks. And then we will update our position and display all of our kinetic energy and momentum and position. Similarities and differences. On the right, you can see that the change in momentum is always 0 in our model. On the left, from our video analysis, there's a slight change in momentum, which this can be explained by the fact that some energy is lost due to factors like sound and friction. Now for kinetic energy in our model, you can see that even though the individual kinetic energies of each block is jumping back and forth, jumping up and down, the net kinetic energy remains constant. So we have no change in kinetic energy, which also agrees with the idea that kinetic energy is conserved. On the left, you can see that there's also some slight decreases, which can be explained by factors like sound and friction. Sources of error. In our model, because we used iterative programming with time steps, we had to include a buffer when we were detecting collisions, which may result in some slight inaccuracies. And now for the physical experiment and video analysis, there might be some slight video quality issues because we took it from YouTube, and also there's energy loss in real-world scenarios. What if one block had a significantly larger mass than the other? Well, as you can see, the same principles still apply. The total kinetic energy is constant, and the momentum, the change in momentum, hovers around 0. What does it mean? How does the change in momentum relate to the change in kinetic energy? Well, the magnitudes of momentum and kinetic energy are both dependent on velocity. The only difference is that if velocity decreases, then the kinetic energy will decrease at a faster rate. Conclusion. We found that the change in momentum equals 0 for all collisions, the change in kinetic energy equals 0 for perfectly elastic collisions, and that energy loss restricts perfectly elastic collisions from occurring in real life.